Thank you very much, and thank you very much to the organizer for organizing this nice conference and for inviting me to present my work. This is a joint work with Benjamin Charlier, Stanley Durleman, Adèle Regimi, Alain Trouvé, and Joshua Sasson. This work is following the idea of diffeomorphometry, as was presented by Laurent just before. So we want to compare two shapes via the diffeomorphisms, transforming the first one into the second one. And the diffeomorphisms that we consider are the final value of the solution of this ODE. So when we have a trajectory of vector fields, we consider the solution here starting at identity and satisfying this equation. Okay. Now, if we want to use this kind of trajectory of diffeomorphisms to register two shapes, what we want to do is minimize this kind of functional, which is a sum of two terms. The first term is a regularization, so you need to define a cost associated to a trajectory of velocity field. And then is a data attachment term measuring how close the transported source is to the target. The framework that Laurent just presented is a large deformation diffeomorphic metric mapping, where you consider the vector field belonging to a fixed RKHS, and you consider L2 trajectories of velocity fields. Then I will not go into the details here, but you have, this is a complete geometric framework, so you have existence of minimum, and you can link this with distance in the shape space. And it gives very nice results. For instance, here, if you want to register the small leaf into the large one, the data attachment term here is defined, the distance here, sorry, it's not, okay. The distance D is defined here with varifolds, so it's the support of the curves that are compared. We do not assume any point correspondence, and here's the kind of result you obtain. So this is a very nice result, of course. However, if you know that your data come from this kind of data here, so the leaf that we observe, they come from a basipetal growth. Here, biologists, so they put some dots on leaves before growth, and you can see that they put them regularly. And then after growth, on the right, the grid of the little dots is not regular enough, meaning that on the left, for instance, you have a basipetal growth. The growth is higher at the base of the leaf than at the tip. The question is, how can we incorporate this kind of prior in the growth pattern in the deformation model? With LDDMM, it's not directly possible because you allow at each time the vector field to belong to the same space. So you have no idea where the base of the leaf is. And if you want to incorporate the fact that your growth is basipetal, you need to at least know where the base is. So in order to do that, you need to incorporate some structure in the deformations that you build. In order, okay, I'm in the wrong, sorry. In order to incorporate some structures, there are two main possibilities. Either you define local field generators, saying you want fields that look like this here or there, or you design a new metric on the vector fields, a metric that is shape-dependent, typically elastic metric. The framework that we design is a mix between these two, where we define a modular way of defining local generators that can be combined, and we define adapted metric. The name of this framework is deformation modules, and I will present briefly how we built it. So in a very simple example, assume that you want to transform the blue square into the black square, and you want to transform them only using local scaling. The strategy here is to consider your shape, so a square, and you extend the space of shape by adding points, because in order to define local scaling, you need to define the center. You could say that you consider only local scaling centered at the mean of your shape, for instance, but here we intentionally dissociate this. So now we have an extended shape, which is made of square and 1 point. And then you need to define what we call a field generator, taking in input a control variable. So you fix a space H of controls, and the field generator will say, given the state of your extended shape, so here the position of your square and point, what are the vector fields that you allow? Typically in this example, it will be vectors. It's always linear with respect to the control, and here it will be the space of local scalings centered at the second component, theta. We need to define cost associated to a particular value of field, and the cost C that we design needs, okay, I forgot V here, but the norm it needs to be controlled by the norm of the vector field in a given space. So we always fix a space of vector field. It will be a scalar Gaussian RKHS in the following, and we define a cost. Then assume that now you don't want to have only local scaling, but you also want to have rotation. You can extend once again the space of shape with a new variable psi, which will be also a point here, saying defining the center of your rotation. So you have a new extended shape which has now 3 components, and the new vector, field generator will take in input 2 controls, 1 scalar for the scaling, 1 scalar for the rotation, and we return the sum of these 2 generated vector fields. And you can combine more and more deformation modules to have more and more complex structures in your deformation model. The trajectories that you will consider then, if O is your extended shape of space here, if O is your extended shape of space, the trajectories that you will allow on your manifold of shape space is the one such that for each extended shape, the speed given, the speed of your shape, is given by applying 1 element of the fibers of vector field that you built via the field generator on your shape. So you only follow trajectories such that the speed of the extended shape is given by applying 1 vector field that this extended shape can build. Okay. No. Now, if you want to perform registration between 2 shapes with this framework, you need to first define the type of modules you want to use. So define extended shape of space. What are the new shapes that you want to build? We call them geometrical descriptor because they capture the geometric information you need to build the structure, to build the vector fields that you want to allow. And then you minimize, once again, a sum of 2 terms. The first one defined by the cost you define in your module, and the second one is the data attachment term. So now, once you have an initial shape, you want to find the best trajectory of control variable, no longer directly vector field, but control variable, minimizing this quantity. Let me show you a first example where you want to transform the blue watch into the black one. And here we use a combination of 3 deformation modules. The first 2 control the pose, so they generate a global translation and a global rotation. And the last one will control the length of the straps of the watch. And we will model it by just local translations, but we enforce that the direction of this local translation are parallel to the strap. So in order to do that, the new geometrical descriptor, so the extension of the shape, is now a combination of points and unit vectors. And we initialize these unit vectors in the direction of the strap of the watch. And we force them to follow the flow because they are part of the geometrical descriptor. So here is the kind of deformation we obtain. Of course, it's not perfect because we really constrained the kind of vector fields we can use, but it's still working a little. However, these deformation modules are what we call explicit deformation modules, in the sense that the expression for the generated vector field, so the field generator, is explicit. Rotation, translation, you can use scaling, you can use all these kind of things, but it's really easy to build. However, it's not so easy to build an explicit formulation corresponding to this kind of growth pattern. This is why we defined another kind of deformation modules that we called implicit deformation modules. Here, the fibers that you put upon each shape no longer has directly an explicit formulation, but is defined from properties that it should satisfy. We once again set a space of control, depending, so giving the dimension of the fibers upon each, roughly the dimension of the fiber upon each shape. And we say that now the vector fields that can be generated given a shape and a control is the one minimizing this kind of quantity. This quantity is the sum of two terms, a regularization term, so the norm of your vector field in a given space. You fix a space and it will be a scalar Gaussian RKHS. And then a quantity corresponding to a constraint. It compares the value of an evaluation operator S, which will evaluate some values of your vector field. So you decide these are the values of the vector fields I am interested in. And then you have the observation operator, which defines the values you want to observe. So now, in order to define your deformation module, you do not need to directly define the field generator, but you need to define the evaluation operator, S, so the values you are interested in, and the observation, the values you want to observe. Once you have done that, you can derive an explicit formulation for your vector field. I will not come into details here. A first example, very easy, is when your shape is just made on point, or the extension of your shape. So your observation operator, and you're interested in the values of your vector field at this point. This is your evaluation operator. I'm interested in the values of the vector field at this point. And the observation operator are the speeds you want to observe at this point. And not surprisingly, what we recover is the sum of local translation. There are some details, we need some convolution of kernel, but it's not very important here. What's important here is that if you want to constrain the values of your vector field to look like this, you obtain a sum of local translations having with the vector roughly the constraints that you enforced. Now assume that you want to observe certain speed, but you also want to have a vector field whose divergence is as low as possible. So this is a current work that I'm doing with Benjamin Charlier. In order to do that, you change your observation operator, which now evaluates the value of vector fields on your points, but also the divergence of your vector field on this point. And as you want to build a vector field that is as divergence-free as possible, what you do is that your observation operator is still the speed that you want to observe, and then zeros. Then the constraint term here can be split in two parts. The first part measures how well your vector field has the speed of your vector field in your point is close to the one you want to observe. And the second one controls the divergence at this point. Of course, if you change divergence with alpha divergence, with the coefficients, you will lower more. If you increase the coefficient here, you will lower more the divergence. So let me show examples of vector fields we can build this way. This is a local translation centered at the center of the grid and with the red vector with a scalar Gaussian RKHS. And here is what we obtain with divergence-free constraint on this grid. So we see that we have something moving that's more divergence-free. Okay. And here's the kind of registration we obtain with the divergence-free constraint of this grid. If you want to register the blue shape into the grid 1, so this is the kind of deformation we obtain. And if we do this without the divergence-free constraint, this is what we obtain. Without constraint, we can see that the motion is mainly vertical, while with divergence-free constraint, you have an opening at the top in order to preserve the volume. we computed the histogram of the infinitesimal areas between consecutive points. So we computed the ratio between these areas before and after the deformation. And we see that with divergence constraint, this ratio is almost 1 everywhere, so we have volume preservation, while it's not true without these constraints. Of course, this formulation can be used in 3D, and we have this kind of the registration. And we still have volume preservation with divergence-free constraint, and which we do not observe, of course, if we do not enforce this. Now, if you want to go further, not only have a divergence-free field, but something that is as rigid as possible. As rigid as possible, I mean here, without local metric changes. So in order to enforce this, we consider in the evaluation operator, the infinitesimal strain tensor, which captures the local metric changes, and it's a symmetric value of the differential. And as previously, the observation operator is made of the speed we want to observe and then 0, and we can split the constraint term here in 2 parts and add a factor exactly the same. This is a usual local translation, and if we add these constraints, we obtain a global translation on the grid on which we have these constraints. If we sum these 2 local translations with this constraint, we obtain a global rotation, which is I want to observe the red values and being as rigid as possible. We can perform registration using this deformation module, and here's the kind of deformation we observe. Of course, without these constraints, it's not what we observe. So if we can compare the grid of deformations. And once again, we can use this in 3D, and here's the kind of deformation that we can build. So there has been many work on as rigid as possible and divergence-free fields, and the goal here is not to build another framework to design this kind of vector field, but is to add new elements to the deformation module toolbox. Because as I said before, we can combine then these deformation modules to build a more complex structure you want to incorporate in your deformation model. Another element of this deformation modules toolbox is what we call implicit deformation modules of order 1. And the goal here is to model growth. The growth will be modeled as a change of the local metric of your shape. So we want to choose specific value for the infinitesimal strain tensor. So now the evaluation operator will be made of evaluating the infinitesimal strain tensor at given points. And the observation operator will be what we call a growth model operator. So it's always linear with respect to h. And it gives a pattern that you want to observe on the points on which you put the constraints. Here, I will give some example of vector fields we can build for different growth operator. We always constrain on the grid of the blue points. And the growth model operator here takes value in families of symmetric matrices. So we can represent them. We have one symmetric matrix at each point on which you put constraint. We can represent them by ellipses where the axes correspond to the direction of the axis are the eigenvectors of your matrices, and the length, if you're positive, it's not necessary, but here it will be positive eigenvalues. It will be represented by the size of the axe of the ellipses. So here you have a uniform growth model operator that enforces a growth that is vertically twice larger than the horizontal growth. And here's the kind of vector fields that we built by minimizing the previous functional. And here's the infinitesimal, deformation that is induced by this. If the eigenvectors are rotated, this is the infinitesimal deformation that you induce. And now if you have a non-uniform growth pattern, you can have this kind of non-trivial deformation given by this non-uniform growth pattern. Here you see that locally you have rotation of your material because of the non-uniform growth pattern. So this means that the principal directions, the principal directions locally at your shape, they can rotate. So what we do to take this into account is that the axis of your ellipse are in the geometrical descriptor. They are put in the extension of the shape so that in the trajectories that you allow, they will follow the integration of the flow. So here the key is to enrich the shape with all the geometric information that you need. Here's an example. If we go back to the as rigid as possible example that I showed before, it's exactly the same, except that the source blue is now thicker. So we combine the as rigid as possible deformation module with an implicit deformation module of order 1, whose gross model operator, so it's constrained on this point, the gross model operator is represented, so it's uniform, and it's represented by the flat blue ellipses. So this means that we allow for the implicit deformation module only vertical scaling, which is uniform. And here is the deformation that we obtain. And if we follow the gross model operator, as we said that the axis of the ellipses follows the flow, they rotate when it's necessary. So the vertical scaling is subjective in a sense, vertical axe attached to the shape. When the shape rotates, the vertical axe rotates also. And we can model growth of a leaf using this framework. This can be interpreted with the idea of morphoelasticity. The morphoelasticity models the growth of an elastic material. So virtually, you split your material in infinitesimal elements, and each element has a growth tensor, but each growth of elements by themselves, they do not allow to preserve the integrity of your material. And then you have an elastic answer of your material to first follow the growth that you impose, but also preserve the integrity of the material. What you do here, and this was well explained in the publication of Nicolas Charon and Laurent Younes, is that you can virtually separate your growth into your vector field in two parts. If you assume that the V growth has here infinitesimal strain tensor equal to your gross model operator, then the penalty that you have here corresponds to penalizing the elastic part of your vector field. Of course, in our model, you can add a penalty that depends on your shape and have linear elastic energy. With this elastic point of view, you can interpret the parameters of the model with the idea of softness of your material. Indeed, if the scale of the scalar Gaussian that you use is very small compared to, so this is due to discretization. If it's very small compared to the size of your mesh, what you will have is that it's easy to satisfy this constraint here. And so this means that it's easy to satisfy a certain growth pattern, so your material is softer. Similarly, if you decrease the new parameter here, you will enforce the minimization of this quantity. So once again, it means that your material is softer. The question now is, can we, with this, recover typical growth pattern that happens with the morphoelastic formulation? This is one example, which is the growing ring. So you have a flat ring such that the outer rim has a uniform growth, so it's uniform, okay? But the inside rim has no growth. And then typically what you observe is this kind of deformation pattern. Can we recover this with the implicit modules of other one that I showed? So minimizing this kind of functional, sorry. The answer is no. Why? Because you have a uniform growth, so your gross model operator takes in input a scalar controlling how much you want to use the uniform growth. And if we wanted to have this, it means that with a space of order 1, because your control is of order 1. So the space of vector field given a shape that you can generate is of order 1. You want to be able to have this kind of folding pattern, but of course, as you have a circular symmetry, if your problem, you can have this part up, but it could be this one, it could be this one, it could be any of them. So you want to generate a vector field that is of maybe an infinite dimension, or at least more than one dimension, a dimension that is strictly higher than 1. But you want to parameterize it with a control of linearly with a control of dimension 1. This is not possible. Typically, what is observed here is a buckling phenomenon. So if you have a small growth, your ring will remain flat. And at some point, if it grows too much, there are too much stress accumulated in your ring. And a small instability, a small noise, will make your ring jump to this kind of pattern, and the part that will go up and the part that will go down will be determined by noise that you have in your data. So we want to incorporate this kind of noise and this kind of possibility of generating multiple patterns, even with a growth that is of dimension 1. This is a joint work with Joshua Sassen. I will not go too much into detail, but what we did is that we use now a field generator that is the sum of two terms. The first term corresponds to the growth. So here you have a control of dimension 1. You have a uniform growth. And the second term is a perturbation of this growth. Right now we use a perturbation as a sum of local translations, but you could use something more complicated and maybe more adapted to elasticity. And the vectors of the local translations is made of two terms. The H here is a control, and so you increase the space of controls here, and you will control the norm of the control. And you multiply also by a term Ti, and Ti will capture how much stress is accumulated by your system. Ti, for each point, it starts at 0, and then it will increase when the value here is increasing, which means it increases when you cannot satisfy exactly the growth pattern. So at first, you can say, at first you have no accumulated stress, so you only generate growth. And if you accumulate stress, you will allow perturbation of this growth pattern. So here is the registration problem. You have a blue ring, and you want to have this folding ring. And we do it with a two-layer ring of control points to constraint. So the outer ring is on the blue ring, and we have an inner ring on which we enforce no growth. On the outer ring, we enforce uniform growth. And here's the kind of deformation we observe. So we do observe this kind of folding pattern. However, if we choose parameter corresponding to a softer material, so as I said before, decreasing the scale of the scalar Gaussian RKHS or decreasing nu, then you will satisfy this constraint more easily, so the stress accumulated will be lower, and you will not be able to perturbate the initial growth pattern. And what we see is that we have a flat growing, but no folding pattern. And similarly, if you choose only a one ring of constraint with uniform growth, but without inner ring of control points, so without growth pattern, you will not have this buckling phenomenon. So to conclude, what I showed is how we can incorporate the, structures in deformation models using deformation modules, and with an implicit formulation that can lead to to rich ensemble of structures you can incorporate. And one key here is always to enrich the space of geometrical descriptor, because the Ti will be formulated as a geometrical descriptor, and a function of a geometrical descriptor here. The goal is to define stress more from elastic energy and maybe to incorporate plasticity. And the question is whether we can, at some point, use this to recover the work of these publications about brain gerification. And you have part of the results that are presented here in our GitHub, and hopefully the full presentation available soon. Thank you very much.
Questions?
So you mentioned here Mahadevan. So I heard 2 or 3 talks by him, and he has similar results, but it seems his methods are much more simple. Do you know how his methods deviate from your method?
Yes, it's elastic formulation with integration of force. I mean, elastic force. So it's really another possibility of modeling this. And right now the goal is to recover this kind of results. And so that's why we're trying to incorporate stress using this kind of neo-Hookean energy. And so yeah, the formulation is here, but we hope that we can use shape analysis tools to then analyze, for instance, the growth of the brain. And in order to do that, we first need to be able to recover their results. So
Mahadevan is the intestines of chicken.
Is what?
Intestines of chicken.
Ah, yes, they did that, yes, also, but also brain gentrification, yes.
I was wondering, by the way, the difference between what Mahadevan or morphoelasticity does and this is the same difference between elasticity and LDDMM. It's you have in one case a time-dependent control and essentially a Riemannian metric or sub-Riemannian metric, and in the other case you just have a one-shot transformation that you want to estimate. But my question was more about. So you showed the last example was, I mean, you knew where to end.
What?
In your last example, you have a target, which was buckling. And what we would like is some kind of growth model that starts with your rings and creates your shape. And so do you know how to parameterize the it's not a geodesic equation, but the optimal control costate evolution so that you would get, by choosing your initial costate, your buckling. Is there a way to go generative rather than matching?
Yeah, I mean, here you have the Hamiltonian formulation if you need. So you can parameterize geodesic by with an initial momentum. You can do that. The question here would be, because we have a growth model, which is uniform growth on the outer layer. That's the growth model. Then there is how this growth model, what kind of pattern this growth model can generate. And here we used a very simple way of perturbating it. But one goal would be to use typically the work of Mahadevan or other people working on elasticity, because they know the kind of wavelengths you would have on the perturbations, the kind of pattern, and we could use this in our model. And then either by choosing trajectories of controls or with geodesic shooting, we can generate trajectories, yes. But I think, yes, we can do this. But the interest of registration is to, for instance, I mean, in the very long-term goal, it would be to, for instance, detect abnormality in growth, and that corresponds to registration.
Hey, so I believe I maybe have understood it wrong. So, but like if I look at your very first example where you have the leaf and you say you don't know where you have like more growth and where you have less growth. I completely agree with this. But how do you, if you then build your deformation model, you need to know exactly where you put more growth and where you allow less growth. So if you apply this to new data point, do you not assume that you have them aligned already? Or
if you, okay, that's of course an excellent answer. So here I did not detail. When you look at the data that we have here, if you have enough data, sorry, let me go back to. If you have enough data, and here you do have some more data given by the dots of the biologists put, you can estimate a gross model. For instance, you assume here you have the dots only on half of your leaf. You can say, okay, I want to estimate a gross model operator that, for instance, we said a polynomial of a certain order, but you can take something else if you're looking for decreasing functions, things like that. And you can simultaneously do the registration on the outer curve, the black dots with landmark identification, and you estimate jointly your gross model operator, a parameterized gross model, and your trajectory. You can also use this to validate a model. You say, okay, assume that we have this kind of growth pattern. Is it realistic or not? Can we recover the trajectory that we observe? But I agree that you would need to have some knowledge. But typically, if you have a template and then you have several data, you know your template, so you know what kind of gross model operator you want to put on your template, and you want to register their model, their data.
Any further questions?
Yeah, so about the explicit and implicit modules, how does it compare in terms of computational cost? Like, because there are examples where you have you can have both, maybe. You can maybe have models with explicit modules or implicit, so you can compare, I guess. And so, how does it compare?
I would say that the main advantage of our method is not the computational cost right now. So we definitely need to improve this. In both cases, we have inversions. Whether you have explicit or implicit, you have inversions. You need to inverse the cost operator. However, we are working on a formulation. I mean, that's the very beginning, but without this inversion. But we need to design an adapted optimization scheme, which is not done at all yet. But that's what I said at the end, but I'm not sure that I had time to really say it. The computational cost is higher for an implicit formulation. But the goal is to lower this cost with a new formulation, but right now the optimization is not working, and we need to design a better scheme, and we're working on it.
Any other questions? All right, let's thank our speaker again.
Thank you.